All right, welcome. Today, we're diving into the invisible rules that run pretty much everything. We're talking about the things that push and pull on every object in the universe. We're talking about forces. So let's just start with the biggest, most fundamental question there is. Forget everything you think you know from science class for just a second and ask yourself, when a force shows up and acts on something, what does it actually do? The answer, in just one single powerful word, is change. That's it. That's the whole game right there. Forces aren't just about moving or stopping. At their very, very core, they are the agents of change. Okay, so what kind of change are we talking about here? Well, a force can change how fast something is going, its speed. It can change its direction, knock it off course. And it can even change its actual shape, kind of like squishing a can. And this whole idea of change leads us straight to the main event for today, the big conflict in the story of forces, the constant battle between what we call balanced and unbalanced forces. Let's break this down. On one side, you've got balanced forces. The best way to think about this is like a perfect stalemate, a perfect tie. The forces are equal and they just cancel each other out. But on the other side, you have unbalanced forces. This is where one force is stronger than the other, and that means there's an overall effect. One side actually wins. This overall effect actually has a name. We call it the resultant force. It's basically the final score after that push and pull conflict is over, what you get when you add up all the individual forces acting on an object. Now, I know that sounds a little abstract, so let's make it super concrete. How do we actually figure out what the resultant force is? Well, let's do a little math. And trust me, it's way simpler than it sounds. Okay, check out this car. Its engine is pushing it forward with a force of 130 newtons. That's just the unit we use to measure force. At the same time, stuff like air resistance is pushing it backward with 100 newtons of force. So what's the overall or resultant force here? Well, since the forces are going in opposite directions, it's just simple subtraction. You just take the big number and subtract the small number. And that leaves us with 30 newtons. But, and this is super important, the direction is just as critical as the number. Since the bigger force was the one pushing forwards, the resultant force is 30 newtons forwards. All right, let's try one more to make sure we've got it. A classic tug of war. The team on the left is pulling with 50 newtons. The team on the right is pulling with 40. What's the result going to be? You got it, right? The team on the left is stronger, so the resultant force is 10 newtons, and it's pointing to the left. That rope is definitely going to start moving their way. And this brings us to a huge takeaway. If you do the math and your resultant force is anything other than zero, that is your proof. That tells you 100% that the forces are unbalanced. Okay, but this next part, this is where things get really interesting, and it's where a lot of people get tripped up. What happens when the resultant force is zero? This leads us to a really surprising truth about how motion actually works. So take a look at this car. It's got 75 newtons pushing it forward and 75 newtons pushing it back. The forces are perfectly balanced. The resultant force is zero. So the big question is, what could this car actually be doing right now? And here's the mind-bending part. There are two right answers. The first one is kind of obvious, right? The car could just be sitting still, not moving at all. But the second one is the real kicker. With those exact same balanced forces, the car could also be moving forwards at a totally steady speed. This is so important. Balanced forces don't mean no motion. They mean no change in motion. Okay, so let's put all these pieces together now. Let's really nail down this fundamental relationship between forces and how an object's speed changes. So what does it really take to make something speed up or slow down? Well, the forces have to be unbalanced. Or you could say it a different way. There has to be a resultant force. Or another way, the forward force has to be bigger than the backward force. See, they're all just different ways of saying the exact same thing. Honestly, this table right here, this is everything. This is the one rule that governs all of it. If your resultant force is zero, what's the effect? No change. The object is either staying still or it's moving at a steady speed. But if that resultant force is not zero, then, and only then, do you get a change. It's either going to speed up or it's going to slow down. Here's a perfect example. A car's got 2,000 newtons of force pushing it forward and 2,000 newtons of resistance pushing it back. Resultant force, zero. The result? No change. The car just keeps on cruising at the same exact speed. But now, look at this. We've got 8 newtons forward and only 2 back. The resultant force is 6 newtons forwards. And the result? The car speeds up. We've got an unbalanced force, so we get a change in motion. It's that simple.
So, if you remember just one thing from all of this, please let it be this. Unbalanced forces cause a change in motion. Balanced forces mean no change. That is the golden rule.
And that leaves us with one last thing to chew on, to really put your new knowledge to the test. Imagine a parachutist. They're falling at a steady, constant speed. It's called terminal velocity. In that exact moment, are the forces on them, gravity pulling down and air resistance pushing up, balanced, or are they unbalanced? Think about it.